Okay, so this is where we left off last time. We were working on a 1D steady state conduction problem involving this cylindrical shell, right? What we had done was derive the differential equation, and then we also had two boundary conditions. And this you can think of as the mathematical statement of the problem. And this is a problem that was easy enough that we could solve it ourselves. In fact, we did last time. But I thought this was also maybe simple enough that it would be a good spot to introduce Maple, which is a symbolic software that you'll probably be glad that you know how to use in this and in other classes. So if you haven't used it before, it's certainly worth learning. So there's just a few things that we're going to have to know how to do when we use Maple, and I'll try to illustrate those in the context of this problem. So let's see. The first thing that we're going to want to know how to do in Maple is enter a differential equation, right? So we're going to want to use Maple to solve differential equations and to do things like evaluate boundary conditions. If I want to solve a differential equation, the first thing I have to do is tell Maple what differential equation I'd like to solve. And that's done with this command called diff, the diff command, right? And the diff command takes two arguments. The first argument is the expression you would like to take the derivative of, right? And then the second one is with respect to what variable. So let's see how this works. So Maple is, again, a software you have access to. Like I said last time, there's a tutorial on the website that you can use. I think if you want to use Maple, at least at this point, you have to use it through XenApp. But that's, it's a pretty easy thing for you to do. So let's look at Maple, if I can find where I have it open. So here's Maple. Maple is a software where you just sort of enter commands in these different lines and they execute sequentially. At least that's how I use it. So the first thing I'm going to do up here is type in restart, and every line in Maple has to be terminated by a semicolon or a colon. We'll talk in a minute about the difference between the two, but this restart just basically means I'm going to clear all the variables. So if there's any variables left over, I just got rid of them. And then the next thing I'm going to do is illustrate the use of the diff command. So, a really easy thing I might want to do is just enter the derivative of a temperature, right? So if I want to do that, I would type in diff and then temperature, which in our case is a function of r with respect to r, right? So the first thing to notice here is that this t, it's temperature as a function of r, right? And I indicate that by using the parentheses r. And then the second argument here is what am I going to take the derivative with respect to, and that's r. And then again here, I can either terminate this with a colon or a semicolon. If I terminate it with a colon like this, it doesn't show me what I just typed. It just enters that, and that's fine. If I want to make sure that what I typed is what I think I typed, which is typically what I'd like to do, I use a semicolon. And if I use a semicolon, then Maple puts out here what it thinks I just typed. And it thinks I typed the derivative of temperature with respect to r, and that's also what I think I typed, so that's really good. So I want to enter the ODE that we have, right? So I'm going to take that ODE and I'm going to assign it to a variable. So we'll do ODE colon equals. That's how we assign things in Maple. And then what I want to do is enter, what is it? I guess it's right here. This ODE right here, right? So I want to take the derivative of r times the derivative of t with respect to r, and that has to be equal to 0. So there's my differential equation. So a lot of times it's nice to do this kind of little by little. So maybe the first thing I'm going to do is take the differential of t with respect to r like that and set that equal to 0. So that's, if I look at this, basically this part of this equation, and then I want to come back up here and multiply that by r. So yeah, that's what I have here. That's now this part of the equation. And then what's the last thing I want to do? I want to take the derivative of this entire thing with respect to r. So I'll come back here and do diff, and then r, there. So now that should be my differential equation, right? It looks a little bit different only because they use the chain rule to expand that, but it's the same as our differential equation. So now I've entered our differential equation into Maple. I've assigned it to this variable ODE so that it just makes it easier to carry around and do different things with it. So the next thing I'd like to use Maple to do is solve this differential equation, right? So we solved it last time. I think we found the solution was something to do with the natural log, and that's fine. You know, Maple is really nice sometimes just to check your work, so we can check and make sure we didn't make a mistake. It's also really nice when you run into differential equations that you're not able to solve. So Maple's really pretty good at that. So let's learn how to do that, and the way you do that is with this command called dsolve, right? So dsolve takes, well, at least one argument, and that argument is the differential equation that you want to solve. So for this particular, where are we at here? For this particular problem, let's get rid of this. The differential equation I want to solve is this thing we assigned to ODE. So I would type in dsolve ODE, like that. And it gives me here, hopefully, exactly the solution that we got. We had a natural log times some undetermined constant plus some other undetermined constant. And if you look in your notes, that's exactly what we got by just separating and integrating, right? So we didn't make a mistake. That's nice. Probably I want to assign this solution to another function. So I'm going to call this TS. And TS is this solution right here, right? So that's how you enter differential equations, and that's how you solve them. And that's in and of itself pretty handy. You can use Maple to do other things. So one thing that we can use Maple to do is evaluate boundary conditions and basically get those two algebraic expressions that we need to solve for C1 and C2, right? This is our general solution. It solves this differential equation no matter what I choose for C1 and C2. I need to pick C1 and C2 such that these two boundary conditions are satisfied. And we can make those substitutions ourselves and do the algebra or plug that into ease if we don't feel like doing algebra. But actually the boundary conditions get more and more complicated, and so Maple can be pretty handy for coming up with those algebraic equations. So if I want to do that, what I need to use Maple to do next is evaluate an expression, right? So I'm going to evaluate an expression, and we do that using the eval command, right? So the eval command takes in two arguments, the first being the expression I want to evaluate, and then the second being at what value of independent variable would you like to evaluate the expression. So here, I want to evaluate our solution at r equals rn and set that result to th. That's an algebraic expression of a boundary condition. I want to evaluate our solution again at r equals r out and set that expression equal to tc. That's our other algebraic boundary condition. So we can use the eval command to do that. So let's go back to Maple here. So I'm going to call one of our boundary conditions BC1. So this is going to be our algebraic expression, and it's going to be eval TS at r equals rn has to be equal to th, like that, right? So what am I doing here? I am evaluating this expression at r equals rn, so it'll just substitute r equals rn here, and I'm setting it equal to th. That should be my boundary condition, and that's what I have here. You can see there's one little, fly in the ointment, and that is that when you use the eval command, you get both the left side and the right side. So it said t at r equal rn is equal to c2 times the natural log of rn plus c1 is equal to th. If I want an algebraic expression that I can actually manipulate, I'd really rather not have this left-hand side that resulted from the eval command. And so that's where I used the RHS, or the right hand side command. So here I just want the right hand side of this eval command, and if I do that, here's my algebraic expression. This guy right here is one of the two equations that I need to solve for C1 and C2, right? And we came up with this last time on our own. It wasn't that hard, but like I said, we can use this to check that, or we can use this for problems that are a little bit harder than this problem. So let's get the other boundary condition. The other boundary condition is basically the same thing, except for now I'm going to evaluate. I'm going to evaluate my solution R equals R out, and I'll set that equal to TC. So there's my other boundary condition. So now I have two algebraic expressions that I would need to solve in order to get C1 and C2. At this point, I could be done if I wanted. I could just copy this and plug it into ease, and copy this and plug it into ease, and hit solve, and ease would solve for C1 and C2. Actually, it wouldn't if I didn't get rid of these underscores, but once I got rid of these underscores, it would. If I actually want an explicit expression, a symbolic expression for C1 and C2, then I need to do a little bit of algebra. And turns out Maple is also really good at doing algebra, right? So we can use Maple for that as well. Let's go back and see how we do that. If we want to solve algebraic expressions, then what I need to use is the solve command. And the solve command takes in two arguments. The first one is what are the equations that you want to solve, and then you want to solve them for what variables, right? So it's just basically going to try to do algebra for you. So in this particular case, the equations I have are these two, and I want to solve them for C1 and C2, right? So I'm going to call these my constants, right? So let's just say constants are equal to, let's solve BC1 and BC2. So those two equations I'll put in curly brackets, BC1 and BC2. And I want to solve them for underscore C1 and underscore C2, like that. Right? So I am solving these two equations for these two unknowns. These two equations for these two unknowns. And hopefully, if everything works, I get an equation for C1 and then another equation for C2, right? And if I want then my symbolic expression for the temperature, I just take these two constants and substitute them back up in here into my solution, right? So that's the last thing that we need to know how to do, which is make algebraic substitutions. So you make algebraic substitutions with the subs command. So I'll take my expressions that I want to substitute, and then I'll put them into some equations. Those are the two arguments. The first one is, what substitutions would you like to make, and where would you like to make them, basically. So for this particular problem, I would like TS to be equal to the substitutions of these constants into TS. Right? So it's going to take, when I hit solve here, it's going to take this variable here, this expression, and it's going to substitute these two expressions into it, and it'll give me TS, but now not in terms of C1 and C2, but rather in terms of, TH and TC and R out and RN. All right. Now I have my temperature distribution. One thing I probably want to do with it is figure out what's the rate of heat transfer, right? So I can do that. The way I would do that is use Fourier's law. Okay, so this is Fourier's law. It basically says, the Q dot is equal to minus K times the area, which is 2 pi r times L times dt dr. We use Fourier's law to derive the differential equation, which we've now solved. So I know what T is now, right? I have T, where is it now? This is my temperature distribution. Now I can use Fourier's law here to figure out what the heat transfer rate is, right? As an engineer, almost always, that's kind of what I'm interested in, is what's the rate of heat loss or something like that. So let's use Maple to carry out this calculation here, right? So how am I going to do this? If I look at this, I have an expression for T, so I'm going to have to use the diff command here, and yeah, I think with that I should be able to get q dot. So let's go back here and figure out what q dot is. Q dot is equal to, again, let's use an assignment, minus 2 times pi, so pi, times r times L times k times the differential of what? The differential of this TS with respect to r. Right? I guess one thing that I'll point out here, and we'll see it again throughout the course, is pi. Pi you can enter as either little pi or big pi. Little pi is actually the number pi. Big pi is symbolic pi. And 99% of the time you want symbolic pi. So we'll put that in. And this is what I get. Once again, when I did this evaluation, it's giving me both what I want and then equals what it ended up equaling. Probably I don't want the left side of this, so I'm just going to take the right hand side of this whole thing. And yeah, there's my heat transfer rate. If I look at this for a second, one thing that pops out to me is that even though this expression had an R here, and of course the temperature is a function of R, right? Q dot is not a function of R. Right? There is no R in here. It's a function of L and K and the temperatures and the inner and outer radius of my cylinder, but is not a function of which R I choose to put into here to evaluate. And that should make a lot of sense, given that our differential equation was based on the idea that dq dot dr is equal to 0. That it didn't matter where I was. Right? If I go back to here. It didn't matter where I was inside of this material. At any value of r, this equation says that dq dot dr is equal to 0. And so, I should be, I think, let's go back to Maple. Too many screens open. I should be, I think, relieved to find out that this expression is not a function of r. Because if it was a function of r, then, I probably would have messed up. So here's the expression for the heat transfer rate through one of these cylindrical shells. Given the geometry, the temperatures that are involved, and then also some material properties, in this case the conductivity. Right? So what we're going to look at next is how do I take this kind of an expression and record the result as a thermal resistance, right? Because thermal resistances, it turns out, are these really incredibly convenient ways of putting a whole bunch of different heat transfer mechanisms on equal footing so that they can be compared. So here's a heat transfer situation. We have a solution, and we'd like to put that solution into the form of a thermal resistance.